Hello everyone, welcome to our new topic in strength of materials. In this video, I will discuss to you one of the fundamental topic in strength of materials. We have here the normal strain. So in this lesson, we will understand the effect of axial loads on a material and compute normal strain of the material caused by that axial load. So these are the objectives of this lesson. But first, let's try to explain what is an axial deformation. So axial deformation, this is the change in the dimension of the material due to the axial load or change in the temperature. So when we have our material, when we have the material here is being subjected to an axial load, again, when we see axial load, that is the load or the force acting perpendicular to the cross-sectional area of our material. So that is our P, no? Or it could either be a compressive force or a tensile force. But due to this axial load, there would be a change in the length. Okay? It's either our length here would increase or decrease depending on the type of load na gi-apply. Like for example, if you have a compression or a compressive force, so obviously there would be a reduction in the length. So what would happen sa ating material? So iikli siya, no? So there would be a decrease in the length. However, if we have a tensile force, no, like for example, if this is our bar, so if there is a tensile force here, so what would happen? There would be an increase in the length naman. So hahaba ang ating material due to tensile force. Now, usually makikita natin ang mga compressive force sa column, while mga tensile force is sa mga trusses. But aside from that, there would be also a decrease or increase in length due to the temperature. Okay, so later on we will tap on that topic, but in this video, we will try to look at on the effect of the axial load alone. So wala pa muna tayong temperature change in this video. Okay? Now, due to the axial load, we have what we call the normal strain. But what is strain? A strain, that is the intensity of a deformation due to the axial load. When we say intensity of a deformation, how large the increase in length or how large the decrease in length due to the axial load. That is that is the definition of strain, or the unit of strain is what we have here, the deformation per unit length. So the change in length in every 1 meter or in every 1 unit length of that material. Okay, so that is the measurement of the intensity of deformation. Now, we have what we call the normal strain. So from the word itself, normal, that is the strain due to the load acting normally or acting perpendicularly to the cross-sectional area. So normal strain is the effect of the axial load, and there is a change in the deformation along its longitudinal axis or the longitudinal length of our bar. Like for example, if this is a bar, okay, then our bar here is being stretched by a tensile load. So our longitudinal axis is this one. Okay, now if there is an increase in the length of our normal or our longitudinal axis, that is what we call the normal strain. We have also the transverse strain, kasi if we are going to stretch our bar, there would also be a decrease in the diameter as well, di ba? Pag i-stretch mo tong bar natin, there would be an increase in the length that is along the longitudinal axis of the bar. However, there would also a decrease in the diameter as well. Okay? So liliit ang ating diameter, di ba? Like for example, if you try to stretch a rubber band, so pag i-stretch mo yung rubber band, what would happen sa diameter sa gitna? Di ba? Iikli yung diameter, so liliit. So that would be the effect of the tensile stress. So there would be two type of strain here. The change in the diameter and the change in the length as well. Okay? Now for the shear strain, that is the deformation due to the shear force. Okay? Now, again, the normal strain is the deformation due to the axial load or the normal force. The shear strain is the deformation due to the shear force. Again, shear force, that is the force acting parallel to the cross-section. And now we have the unit or the formula for normal strain. We have the strain is in terms of epsilon, this is epsilon, which is equal to the axial deformation, or that is delta. Okay, delta here, that is the axial deformation over the L. Our L here is the initial length. Now, if this is our bar is being stretched by a tensile force T. This is the original length, this L here, this is the original length. But due to the tensile load, we have an axial deformation or the increase in the length. So therefore, we have our normal strain here, which is equal to the deformation over the original length. Now, for our sign convention, if you have a positive value of deformation, that means that our material is getting longer. Okay, so there is that is tensile strain. Now, if it has negative value, that means that our material is getting shorter, or that is a compressive strain. Okay, since compression makes our material shorter. Hence, we have the unit here of our normal strain, which is in terms of meter over meter, since this is the deformation over the original length, or it could also be millimeter over the millimeter. Okay? Now, therefore, we can cancel this out, diba? Since these are equal, or these are the same measurement or the same unit, so we can cancel this out. So we have unitless here, but for normal strain, we should always include the unit, such as meter per meter or millimeter per millimeter, or we could also have inch per inch. Okay? Now, to simplify this one, we have the unit 1 micro epsilon. Okay, this epsilon here, or micro strain, so which is a micro, this means that it's 10 raised to negative 6. Okay, so 1 micro epsilon is equal to 1 times 10 raised to negative 6. Again, this one is the micro. Then the strain is millimeter per millimeter, or it could be meter per meter, or it could be inch per inch, or foot per foot. Okay, so this is the unit of our strain. So let's try to apply this formula by solving problems. I have prepared examples. We have an example here. A steel bar with a 25 feet length is subjected to a tensile load. The change in length of the bar is 0.625 inch. Compute the normal strain in the wire. So to better understand the problem, we need to draw it. Okay? So i-draw na to siya. So we have steel bar, and this steel bar here is subjected to tensile load. Let's say it's T. Now the length of this bar is 25 feet. Since a tensile load siya, so there would be an increase in the length. So we have, which is 0.625 inch. Now we need to compute the normal strain. So by using the formula, we have the strain, that is in epsilon, is equal to delta over the original length. So we have the strain is equal to, now our deformation is 0.625 inch. So we have 0.625 inch over, our length is in terms of feet. We have 25 feet. So we need to convert that into inch. So we need to be consistent with the unit. So 25 feet times, there is in 1 foot, there is 12 inches. So we have the length here, which is 300 inches. Okay? That is the length of our bar in terms of inch. So we divide it by 300 inches. So we have the normal strain equals to 2.083 times 10 raised to negative 3, that is inch per inch. Okay? Now, take note, we need to simplify it further by expressing it into micro. Now, just to make it short lang, just to eliminate 10 raised to negative 3. So, we move 3 decimal places to the right. We have 2,083 times 10 raised to negative 6 inch per inch. Now, we know that times 10 raised to negative 6 is in micro. So, we have strain here, which is equal to 2,083 micro. Now, inch per inch, that is in terms of epsilon, tama? Or that is strain. So, we have micro epsilon. That is our strain. So, this is our answer for the first question. This normal strain here, this result here, explains that in every 1 inch of the bar, the deformation is 2.083 times 10 raised to negative 3 inch. So this is the amount of deformation for every 1 inch of the bar. So that is the concept, or that is how you explain normal strain. Now we have our second example. A compression test was conducted to a 200 mm diameter and 400 mm long concrete specimen. It was found out that the concrete fails when the normal strain is 1,200 micrometer per meter. Determine the maximum change in length that the concrete can tolerate before failure occurs. So we have a concrete specimen. No? This is done when you want to determine the compressive strength of our concrete. Kung gusto mong malaman yung gaano ba kalakas yung ating concrete. So we have a cylindrical specimen. This is concrete is tested using a machine, a universal testing machine. So ang ginagawa dyan, ang concrete is being subjected to an axial load P. Okay? Now, this load P here determines the maximum capacity of our concrete. The usual dimension that is being used for concrete test is 200 mm diameter, this one, millimeter diameter, and 400 millimeter long. Okay? Now, this specimen is being subjected to load P until such time that our concrete fails. Now, it was found out that during the failure, the recorded normal strain is 1,200 micrometer per meter. Now, if there is a compressive force, obviously, our concrete would have a decrease in the length. Okay, so there would be a decrease in the length. So this would be the final length of our concrete. So there would be a deformation in terms of delta. Okay, now our task here is to compute for the delta during the failure. So we have to use the normal strain formula, which is the epsilon, or the normal strain is equal to delta, or the deformation over the original length, which is the epsilon here is 1,200, that is in micro meter per meter, is equal to the unknown deformation over the length. The length here is the original length. So the original length of our specimen is 400 millimeter. That is the longitudinal axis of our specimen. So we have, now take note, since this is in meter per meter and we have our length is in millimeter, we might not need to convert this one since it can be cancelled out, diba? Since meter over meter can be cancelled out. So we need not to convert 400 here into meter. Okay, so let's stay that as millimeter. So we have 1,200 micro epsilon, we have 1,200. Now micro is times 10 raised to negative 6 is equal to the deformation over the original length, 400 millimeters. So we have here the deformation, the maximum change in length during failure, which is equal to 0.48 millimeter. So this is the deformation before our concrete cracks or our concrete fails. Okay, so we have that answer as our final answer. Now for our last example in this lesson, we have two steel rods supports a rigid bar ABCD. So we have two steel rods, we have rod 1 and rod 2. Now this rod here supports a rigid bar ABCD. When we say rigid, our bar would not have any deflection. Okay? Now, we have our bar here which is fixed. Okay, then at this point, no, connected sa B and C. Then during the load or before the load is applied, so before we put a load at D, okay, so there were no strain. So therefore, walang mangyayaring deformation before the load P is applied. However, when the load is applied, rod 2 here has a normal strain of 800 micro strain or micro epsilon. So we have the rod 2 here, the strain which is equal to 800 the micro epsilon after the load P is applied. Now, our first question here is compute the actual normal strain in rod 1. So we need to compute the strain in rod 1 given the value or given the normal strain of our rod 2, which is 800. So how are we going to compute this one? Now, so if we try to put a load P, so the deformation would be this one here. Now, this red line here, this is our rigid bar. Now, this would be the deformation of bar 1. This would be the deformation of bar 2. And this is the movement of our point D. Okay? Now, as what you can see, now take note, I drew it exaggeratedly para ma-imagine nyo lang kung ano ba yung deformation ng ating rigid bar. Okay, once we applied load. So this is an exaggeration. So if we put a load P again, so this would be the diagram or the deformation diagram. The deformation of bar 1, that is the increase in length of bar 1. Obviously, there would be an increase. And this one is the increase in length of our bar 2. Okay, since this is the new connection, this is point B, the new point B, and this is now the new point C. This is after the load P is applied. Now we know that bar 2 here has a normal strain of 800 micro epsilon. So we can actually compute for the deformation at 2, this one here. How are we going to compute this deformation? So we just need to apply the formula, the strain is equal to the deformation over the original length. Now, our strain here of bar 2, this is for bar 2, which is equal to 800 times 10 raised to negative 6, since that is in micro, which is equal to the deformation, which is unknown, that is deformation 2 over the original length of 2. Okay, this original length of 2 here, which we know that our original length of 2 is 2.7 meters. And 2.7 meters can be expressed as 2,700, which is, if you want to convert it into millimeter. Tama? So we have 2,700 millimeters here. So we have the deformation of bar 2, which is equal to 2.16 millimeters. So we know that this height here is 2.16 millimeters. Okay? So our goal here again is to compute for the strain of bar 1. But before we can compute the strain of bar 1, we need to compute first the deformation of bar 1. Okay? Now, how are we going to compute for deformation of bar 1? So we have here a similar triangle, diba? Or ratio and proportion. So we can express the relationship of the deformations with respect to their reference or the length from point A. Okay? Now we know from A to B we have 2,000 millimeters, tama? And from A to C, we have 2 plus 2.5, we have 4.5, correct? So we have here this length, which is 4,500 millimeters. So we can use ratio and proportion here. We have deformation of bar 2 over 4,500 equals to the deformation of bar 1 over 2,000. Okay, just use ratio and proportion to this one. So we have the deformation of bar 2, which is 2.16 over 4,500 equals to the deformation of 1 over 2,000. Now, we know that this one is in millimeters, this one is in millimeter as well, so we can cancel this out, and 2,000 is in millimeters, so we have our deformation here, which is in terms of millimeter. So, our deformation of bar 1, which is equal to 0.96 millimeters. So, this one here is 0.96 millimeters. Okay, so we have now the deformation of bar 1, correct? So we can now compute the normal strain of bar 1 by applying this formula again. So we have normal strain of bar 1 is equal to the deformation of bar 1 over the original length of bar 1. We have the normal strain of bar 1, which is unknown, equals to the deformation of bar 1 is 0.96 millimeter over the length of 1, the original length of bar 1, which we know that is 1.5 meters, or that is 1,500 millimeters. So we have the normal strain of bar 1, which is equal to 6.4 times 10 raised to negative 4 millimeter per millimeter. To express this into a simpler form, so we use micro. Now, to convert this into micro, we move 2 decimal places to the right para for it to become negative 6. So we have 640 times 10 raised to negative 6. That is in epsilon, since millimeter per millimeter is in epsilon. So we have the normal strain of bar 1, which is equal to 640 micro strain or micro epsilon. So this is the answer for letter A. Now for our question letter B, if there is a 1 millimeter gap in the connection between the rigid bar and rod 2 before the load P is applied, compute the normal strain in rod 1. So again, if there is a 1 millimeter gap in the connection between the rigid bar and rod 2. So therefore, if we try to zoom this area here, this point here, point C, we could have seen a 1 millimeter gap. So there would be a 1 millimeter gap before rod 2 is connected to point C. So our 2.7 here is up to this point only lang. Okay, so this one is in 1 millimeter gap. So we need to compute the normal strain in rod 1. So same question, but the only different lang is that we have 1 millimeter gap at point C. So in this case, we can compute, or the same procedure we need to compute for the deformation of rod 2. So the deformation of rod 2, we have still the formula. The strain is equal to the deformation over the length. The strain is 800, the micro times 10 raised to negative 6 equals to the deformation over the length, which we know that is 2,700. So we have the deformation, so we have the same answer from the first one. We have here 2.16 millimeters. Now take note, the total movement of point C is equal to the deformation of rod 2 plus 1 mm, correct? So this one is the deformation of rod 2 plus the gap 1 mm. So that would be the total movement of point C. So from this point to this point, we have the movement of deformation of rod 2 plus 1 mm. Okay? Now, so therefore, we can say that the entire deformation or the entire movement of point C is equal to 2.16 plus 1 mm, correct? So we have 2.16 plus 1, we have 3.16 millimeters, correct? So this is the height or the movement of point C. So at this point, we have 3.16 millimeters. Now, to compute for the normal strain of 1, we have to compute first again the deformation of rod 1. So we have the deformation of rod 1, which is equal to, by using ratio and proportion, we have deformation of 1 over 2,000 equals to, now in this case we have 3.16 millimeter over the distance of point C from point A, we have 4,500 millimeters. So we have deformation of 1 equals to 1.404 millimeter. So we again compute for the normal strain. We have the normal strain equals to the deformation of rod 1 over the original length of 1, that is the normal strain of 1, equals to the deformation, which is 1.404 over the original length, which is 1,500. So we have the normal strain of rod 1 equals to 9.363 times 10 raised to negative 4. Now the unit is in millimeter per millimeter. So millimeter per millimeter. So we have the normal strain equals to, again, to make it simpler, we adopt the micro. So we move 2 decimal places to the right since times 10 raised to negative naman siya. Times 10 raised to negative 4 already. So we have 936 micro strain or micro epsilon. So this is our final answer for question letter B. And that ends our lesson in normal strain. I hope to see you in my next video. Thank you guys for listening and God bless.